Hello everyone, I'm Camillo Quattrocchi from the University of Catania. Today I will present the work titled Synchronization is all you need, exocentric-to-egocentric transfer for temporal action segmentation with unlabeled synchronized video pairs. As we know, transferring knowledge from one domain to another is still an open challenge. Specifically, we know that a system trained on third-person data, called exocentric data, would struggle to work on data acquired from a first-person perspective using wearable devices, called egocentric data. For example, a company may have collected exocentric data from fixed cameras and trained their temporal action segmentation models to monitor their production processes. At some point, the company might decide to purchase wearable devices to acquire egocentric data and adapt their algorithms to the new data. This process is not simple, as it requires acquiring new data, labeling it, and retraining the models. As we know, labeling video data is a time-consuming and resource-intensive process. In this work, we propose an adaptation methodology based on a labeled EgoExo video pairs that leverage the technique of knowledge distillation. The methodology was validated on two datasets, Assembly101 and EgoExo4D. The main goal of the methodology is to adapt a temporal action segmentation model from the exocentric view to the egocentric view using unlabeled EgoExo video pairs. The methodology incorporates a combination of feature extractors, namely TSM and NV2, and a temporal action segmentation model called C2F-TCN. Within the proposed methodology, knowledge distillation is used at two different levels. At the feature level, where we aim to extract the same feature from the feature extractor regardless of the ego or exo view, and at the model level, where we aim to align the internal representation of the two ego and exo models. The dataset used to validate our methodology share the characteristics of being procedural video datasets. The first, Assembly101, contains synchronized EgoExo videos of users assembling toys, while the second, EgoExo4D, contains videos of users performing various procedural activities from different points of view, including the egocentric one. Let's take a closer look at the pipeline of our methodology. Initially, at step 1, a fixed camera captures third-person data, which is then temporarily labeled and used to train a temporal action segmentation model called EXO model. Then, at step 2, egocentric data is acquired from wearable devices. When these new data are used with the previously trained model, the resulting temporal segmentation will obviously be poor. At step 3, the adaptation phase from exo to ego view begins. Specifically, two synchronized exo and ego view streams are captured. These new video streams will not be labeled. Defining the old exo model as the teacher, we define a new student model called ego model. During the adaptation phase, the video streams are passed to the corresponding models, and the prediction of the exo model are used by the ego model through knowledge distillation techniques. At step 4, we can see the new ego model making correct temporal prediction, even though it has never seen any labeled egocentric videos. During the distillation process, the student is optimized to mimic the outputs of the teacher component. This process is carried out using an adaptation set composed by synchronized ego-exo video pairs. No ego or exo labels are used at this time, with the only supervision being given by the exocentric video passed through the fixed teacher. We consider two adaptation steps that can be either included separately or combined: feature distillation and model distillation. In feature distillation, we encourage the student model to extract from the ego videos representation similar to the exo one extracted by the teacher model, while in model distillation, the aim is to distill the student model to make its internal representation similar to those extracted by the teacher model on the paired exocentric videos. Here are the results of the Assembly101 dataset. For each feature extractor, experiments were conducted using the two distillation methodologies individually or combined. In general, the model using feature extractor with NV2 performs better in any level of distillation used, achieving a 15.99% improvement in terms of edit distance compared to the model that does not use any adaptation technique. Here are the results on the EgoExo4D dataset. All experiments refer to the feature extracted with NV2. Here, we explored both the exo to ego transfer and the ego to exo transfer, achieving a best results of a 4.44% improvement in terms of edit distance. The smaller gain compared to the experiments on the Assembly101 dataset is due to the higher complexity of the EgoExo4D dataset. In conclusion, the main contribution of this work is the development of an innovative methodology for adapting from the exocentric to the egocentric view for the task of the temporal action segmentation, demonstrating the effective contribution of knowledge distillation when using synchronized EgoExo video pairs. Thank you for your attention.